Rebecca, how you doing?
Hi Chris, not bad. How are things with you?
Oh, getting there.
I was hoping to see you actually. I wanted to have a chat with you about the students and diagrams. They just don't get them. Some students aren't putting them in the assignments at all and are missing out on a lot of marks because of this.
So what are they saying?
They're saying they don't understand what to put into the diagrams and they don't feel they need them to solve the problems. They don't know what we're looking for, and when they only get half marks, they don't know what they did wrong. But generally it's just, why do we need diagrams anyway?
Sounds like they don't understand that they're a form of communication. Diagrams are part of the engineers and scientists' toolbox. It's like a carpenter. A carpenter has specific tools for doing specific things. And sometimes they modify some of the tools, and they have some tools that they have to develop completely from scratch. Let me show you, come on. You might start off with something like parabolic motion. Okay, this is one of the standard sort of diagrams that you have. Okay, this is what's going on in the x direction or time. This is what's going on in the y direction above us. Tell me what that means to you.
Parabolic motion with no air resistance.
What's parabolic motion mean?
Well, we've got constant velocity in the x direction and constant downward acceleration in the y direction.
Okay, and how do you know it's got no air resistance?
Because it's symmetrical, so there's no energy loss.
What would happen if there was air resistance?
If there was air resistance, then the velocity would be decreasing and the projectile wouldn't travel as far.
Excellent. What other assumptions have we made for this diagram?
The projectile isn't traveling in a resistive fluid, such as water.
So there's no air resistance, no fluid resistance, yeah? What else?
That it's being affected by gravity.
Good. What would happen if it wasn't affected by gravity?
Then the projectile would just keep moving in the direction it started out at.
So we've got here a basic diagram. We've modified it for air resistance. We've modified it for no gravity. We could modify it even further. So it could be modified for if we were firing up at something, or maybe we're standing on the top of a building and we're throwing a ball straight out and it will be pulled down by gravity. Or perhaps trying to get a basketball into a hoop, so the hoop could be here and we could go up and let it drop into the hoop. All these are just modifications of our standard diagram. How did you learn about diagrams?
Well, just lots of practice, really. Working through the problems along with the lecturers and copying out the diagrams, trying to understand why they use them and doing them in the assignments. So what other diagrams should be in the toolbox?
Well, the students are doing mechanics, so the types of diagrams I would put in there would be things like something that was balanced forces, perhaps like this, just a box on a bench with the downward force, the upward force, the accelerating force and the frictional force. You could extend that to putting it on a slope. You might then even have it so that it was connected to a pulley, and we could do that as well. So just imagine, visualize for yourself an apple in a tree. Okay, the apple's sort of wobbling there on the tree, the wind's blowing just like it is today, and it falls down, hits the ground. And you could abstract that a little bit to make it a cartoon. You can see, visualize the cartoon? Yeah, okay. But that's still not a diagram, it's still a picture. Perhaps if you take away the tree and you make the apple a square, and you can do that. So you can make it a circle.
Yep.
You could make it a triangle.
Yep.
It doesn't matter, it's just some object. So in taking away all this other stuff like the wind and the wobbling in the tree, you've created now a diagram that just tells us about the energy that's going on of this apple falling down. What do you think should be in there?
So what about conservation of energy?
Yeah, all right, well show me.
Well, just a basic one could be an object at a height, which then has kinetic energy as it falls.
Good, that was like our apple from the tree.
Yeah.
Okay, let's say we put a bed under the tree to catch the apple.
So, like a spring?
Yeah.
Yeah.
Excellent. So that's why we want students to learn diagrams, so that they understand the basic principles. But that's only part of the story. So you know yourself what diagrams are. Do you think you can help the students with this?
I think so.
Excellent. And what are you going to tell them?
There are a lot of different diagrams that they can have that they can modify if they need to fit their situation, like we did here with the air resistance.
So they just need to grab a few diagrams and stick them in their toolbox.
Yeah.
Excellent.
And lots of practice.
Lots of practice.